Right now, inside the device you are watching this on, a tiny machine is following the same 3 steps, over and over, billions of times a second. Let us slow it all the way down and watch it work. This is a processor, the brain of any computer. We measure its speed in gigahertz. 3 gigahertz means 3 billion steps every single second. That number is almost impossible to feel. So here is the promise. By the end of this video, you will understand exactly what the processor is doing in each of those steps. And it is simpler than you think. It all comes down to one repeating loop. Let us start at the bottom. A program, any program, is not magic. Once it is loaded, it is just a list of numbers sitting in memory. Memory is a long row of numbered slots, and each slot holds one number. That is it. Your web browser, your game, your operating system, while they run, all of it is just numbers in numbered boxes. The processor's whole job is to read these numbers and act on them. So how does a number become an action? Look closely at one of them. The processor reads it in binary as a pattern of bits, of ones and zeros, and that pattern is split into parts. The first part is the opcode. The opcode is the verb. It says what to do, like add or load or store. The remaining parts are the operands. They say what to do it to, usually which registers to use. So this one number means add register 1 and register 2 and put the answer in register 3. One number, one instruction. To run that instruction, the processor uses a handful of parts. Memory, on the left, holds the program and the data. The program counter, or PC, holds the address of the next instruction to run. The instruction register holds the one we are working on right now. The control unit reads the opcode and flips the right switches. The registers are a few tiny, extremely fast slots for the numbers in use, and the arithmetic logic unit, the ALU, does the actual math. Keep this map in mind. Everything now flows between these boxes. Now the loop begins. Step 1 is fetch. The program counter holds an address. The processor sends that address to memory and says, "Give me what is in that slot." Memory hands back the instruction, and it lands in the instruction register. Then immediately the program counter ticks up by 1, so it already points at the next instruction. That is fetch. Go get the next instruction and take a step forward. Nothing has been done yet. We have only collected the order. Step 2 is decode. The instruction is still just bits, so something has to make sense of it. That is the control unit. It looks at the opcode and works out what this instruction actually means. Then it switches on exactly the hardware needed. Here the opcode says add, so the control unit tells the ALU to get ready to add, and tells the registers which 2 to read and which 1 to write. Decode does not move any data yet. It sets the path. Think of it as throwing the switches before the train runs. Step 3 is execute. Now everything actually happens. The 2 values flow out of the registers and into the ALU. The ALU adds them. 7 plus 5 is 12. Out comes the result. And in the final move, that result is written back into the destination register. The work is done and stored. Fetch got the order. Decode understood it. Execute carried it out. 3 steps and 1 instruction is complete. But a program is not one instruction. It is thousands or millions. So the processor does the only sensible thing. It goes back to the start. Fetch the next one, decode it, execute it. Again and again. This is the fetch, decode, execute cycle. One lap of this loop is one instruction. And the processor runs lap after lap without ever stopping for as long as the power is on. Let us watch a real, tiny program do something useful. Add 2 numbers A and B and store the result in C. First instruction, load A from memory into register 1. The cycle runs and register 1 now holds 7. Second instruction, load B into register 2. Now it holds 5. Third instruction, add register 1 and register 2 and put the sum in register 3, 12. Last instruction, store register 3 back into memory into C. 4 instructions, 4 trips around the loop, and the computer has added 2 numbers. Every calculation you have ever seen is built from steps this small. There is one more trick, and it is a big one. So far the program counter just steps forward, one by one. But what if you want a loop or an if statement? For that you need a branch. A branch is an instruction that writes a brand new address into the program counter. Watch. This one checks a counter, and if it is not yet 0, it jumps the program counter back to repeat the body. The counter ticks down 3, 2, 1. When it hits 0, the jump is skipped and the program moves on. Changing the program counter is how every loop and every decision in software exists. What keeps all of this in time? A clock. Not a clock that tells the hour, but a signal that ticks. On, off, billions of times a second. Every tick nudges the machine one step forward in perfect lockstep. This is what gigahertz measures. 3 gigahertz is 3 billion ticks per second, which means each tick lasts about a third of a nanosecond. That is the heartbeat. The faster it ticks, the more steps per second, and the faster your computer feels. One last idea, because real processors are cleverer than this. Each instruction passes through stages: fetch, decode, execute, and a couple more. In a simple design, you finish one instruction completely before starting the next. That wastes hardware. So instead, processors overlap them like an assembly line. While one instruction is executing, the next is being decoded, and the one after that is being fetched, all at the same time. This is called pipelining. Each instruction still takes several steps, but now one finishes every tick. Real chips push further still, running several of these lines at once, and guessing which way branches will go to keep them full. And that is the whole secret. Fetch, decode, execute. 3 plain steps, repeating billions of times a second. The next time your computer does something that feels impossibly fast, remember, underneath it is just this loop, running one tiny instruction at a time. Now you know exactly what it is doing.